So welcome to this session on symbolic methods in natural language processing. Last time we saw many methods for describing syntax. So we saw formal languages described by formal grammars. We saw a special case of formal languages called regular languages that can be described by regular expressions and finite state automata. We also saw push-down automata that are able to describe context-free languages. And we finished with this slide on tools to make compilers using formal languages, regular formal languages. Here is a slide giving just one example of a context-sensitive language. So this is one step of complexity higher than context-free languages. And this is a language which is quite easy to describe to a human. We want every word to be of even length, and the first half of the word should be identical to the second. So it's very easy to describe, but you cannot describe this language neither by a regular nor by a context-free grammar. So you need a context-sensitive grammar. And here it is. I'm taking the alphabet 01 for simplicity. I'm giving some rules. And as you can see, these rules involve the context. So here we have E that remains, but E should be preceded by A2. Here we have F that remains, and so on. So if you take some time and look at this, you will see a general method of applying these rules and pushing information to the left and obtaining the same expression on both sides. And you see how complex it is to obtain this very simple word 0101. So this is just an example. Here I have some slides on visual grammars. We don't have time because today we will talk about the logic, and this is a difficult topic, and I will take some time to explain. So this, you can look at it if you have some spare time. It's a generalization of Chomsky grammars, and we introduce more than one concatenators. So concatenation operators. In the case of Chomsky grammars, we have only one concatenation operator. I can call it next. And this is equivalent to the description of the word Abba, where I have two occurrences of letter A, two occurrences of letter B, and the fact that the first B follows the first A, the second B follows the first B, and the second A follows the second B. So in here, there is no more information than in there. But of course, by using different concatenators, I can describe, for example, this visual diagram. And there are many people working on diagrams. There is even a conference every 2 years on diagrams. And they, of course, use methods like these. Okay, so let us move to the next important topic of this thread, which is the topic of the notion of formal system. So intuitively, a formal system is a formal language plus a deductive system. In this formal language, I have a set of sequences, so a set of words of the language, which I call well-formed statements. So if I take only well-formed statements, I get a language. And the deductive system, which is new, is a way to build new well-formed statements out of existing well-formed statements. Some of the well-formed statements are not built using the deductive system, and they are called axioms. So if you want a formal system, then you need to have an alphabet. You need to have some rules saying what is a well-formed statement, so which words out of this alphabet are part of your language. Then some of these words you will call axioms, and then you need inference rules to build more well-formed statements, potentially infinitely many well-formed statements out of your axioms. Okay. So this means that we have two kinds of rules. We have rules that give us the fact that some word is a well-formed statement. So rules describing a formal system as a formal language, and rules providing us with new well-formed statements, which we call inference rules. So a typical example is in mathematics, you have formulas. Your alphabet is the set of all symbols you use in your formulas. Well-formed statements are mathematical formulas that are syntactically correct. So for example, A equals to B is syntactically correct. A, B equal is not a syntactically correct formula. So well-formed statements are, in this example, formulas written correctly. Now, you know that in mathematics, you have axioms, and inference rules are the rules you use every time you take a formula and write the formula implies this other formula. By using implications out of your axioms, you obtain new formulas, and these are called theorems. And you can have an infinite amount of theorems out of a given set of axioms and using given inference rules. And this is exactly what a formal system is. Now, inference rules take 1 to n statements or formulas, it's the same thing, and provide a new statement. So this is a way to write an inference rule. On the top, I put the input formulas, and then at the bottom, I put the output formula, which is always a single one. And here I write the name of the inference rule. Another way of denoting this is by this symbol, which means deducing G from F1 to Fn through the inference rule R. A proof is a repeated use of inference rules to selected formulas to obtain some formula. So to prove A, I start with axioms. With these axioms, I apply inference rule and I get formulas, and then I apply inference rules to the formulas and so on until I get A, and this is the proof of A. So this is how we prove a theorem, and when we prove something, we call it a theorem. Now, we will deal with a specific case of formal system, which is first-order logic. And in a forthcoming lecture, we will see other formal systems. For the moment, let us concentrate on this one, first-order logic. Now, what is the alphabet of first-order logic? You have predicates, functions, variables. These are the parts that are, in some sense, lexical. It means that you can give them names. You can have as many as you want, and you can use them in formulas. And these are the parts that are grammatical in some sense. They are symbols that have a single meaning in first-order logic, and you cannot change it. Now, what is the difference between predicates and functions? The difference is that predicates are used on the highest level. If you take just a predicate, it's already a formula. A predicate can have arguments. The number of arguments is called the arity of the predicate. And these arguments can be either variables or functions applied to variables. And when I take variables and I apply functions and then functions to other functions, I get terms. So we have two very distinct things. We have predicates and we have terms. Terms are arguments of predicates in a formula. You cannot take just a term and call it a formula. It's not a formula. So you have your predicates at top level only. You can combine them, but still at top level. How do you combine them? You combine them with connectors. So these connectors can be negation or implication. And inside predicates, you have terms, which will be functions, variables, and so on. A universal quantifier is applied to variables only. Then we have the sign of equality, which is used only between terms. And then we have parentheses. Parentheses can be used at any level. We will see all of this in more detail. We will see examples and everything. Now, how do we make statements out of these ingredients? There are three modes of reasoning: deduction, abduction, and induction. Deduction is what is used in science. If we have A that is true and A implies B, then B is true. This is an inference. It has a name. It is called modus ponens. And it's a mode of reasoning called deduction. Abduction is saying that if B is true and A implies B is true, then A is true. Well, this is not always the case. So here I have an example. If donkeys are living creatures and the professor is a living creature, then the professor is a donkey. Okay, so this is sometimes true, but not always. It's a way of reasoning which is not scientific. So why do we mention this? Because it can give us a hint. Same thing for induction. So abduction and induction give us hints on how to investigate the real world, but they are not scientific methods of proving something. Even though politicians use abduction and induction a lot. Here is an example. All felids are mammals. So felids are félins and mammals mammifères. So all felids are mammals. A cat is a felid. I deduce that a cat is a mammal. So we all agree on that. The other way around, all felids are mammals. A cod is cabillaud, is not a mammal. Therefore, a cod cannot be a felid. So you see, this is going the other way around with a negation. So we call this modus ponens and not popens. This is an error, modus ponens, and this one modus tollens. And we all agree on that. Now on the next slide, I'm using words you don't know. You don't know because they don't exist. But even though these words do not exist, you do agree on the validity of the reasoning. All blasias are casomers, an elithiotis is a blasia, therefore an elithiotis is a casomer. All blasias are casomers, an exhypnate is not a casomer, therefore an exhypnate cannot be a blasia. So reasoning is still valid, even though I don't know the meaning of these words. And this calls for formalization. So formalization is representing reasoning by symbols. And here you see the symbols P and Q are predicates. We are at top level of the formula. I have predicates combined by an implication, and I have a quantifier applied to a variable. I call this variable X. It's the most natural name for a variable. And I say for all X, Px implies Qx. So P can be blasias, Q can be casomers. And then I take a special case, an elithiotis. I call this A. And I'm saying P of A. So an elithiotis is a blasia. My deduction is that I have that an elithiotis is a casomer because all A is Q, because for all X, Px implies Qx. And same thing here. I have not QB, and this implies not PB. Because if I had PB, then I would also have QB. And this is what we are going to do. We are going to formalize reasoning by using this formalism of first order logic. Now, what is formalization and why do we need it? In many disciplines, you have already encountered the terms of data, information, and knowledge. And these words are not used with the same meaning in different domains. In the domain of artificial intelligence, these are technical terms, and they have a specific meaning. So data are sets of numbers, since you are using numeric equipment. And data, we know where it comes from. It comes from sensors or simulation programs or random data generators, but we don't know what it means. Once we know the meaning of our data, it becomes information. So information is data plus a specific meaning for every part of data. Now, what is knowledge? Knowledge is something that allows us to do predictions. So it's patterns or tendencies in data and in information. So example, let us take the Brest railway station. I put sensors, cameras, microphones, photoelectric cells, and so on. These sensors sent me numbers. These numbers are data. Now, once I know that a specific sensor sends me visual data, images, I can recognize things in these images. For example, I can do optical character recognition and read on the side, on the label of the train, where the train is going to, what is its identifier, when does it leave, the number of the wagon, the class. All of these are pieces of information. So this is called information extraction. I took the data, image, and I extracted textual information. I got information. Now, this is not yet knowledge. Now, every day, I do the same information extraction, and I notice that every day besides the weekend, there is a train with the same identifier, same destination, leaving at the same time, more or less, with some seconds or minutes of difference of offset. So if this happens regularly, I can predict that it will happen tomorrow, because tomorrow is not a weekend. The information I got forms a pattern that allows me to do a prediction. That's knowledge. And artificial intelligence likes to grab and represent information, but also knowledge. To represent knowledge, we need a knowledge representation language. And the formalism we saw here is a knowledge representation language. So this allows us to represent not only information, but also knowledge extracted from information. And we will see how. Once you have knowledge represented by some knowledge representation language, you can do inferences. You can do reasoning. And reasoning means get more information, get more knowledge out of the one you have represented already. And we will see many knowledge representation languages allowing us to build what we call knowledge bases. So a knowledge base is a place where we have gathered information and knowledge. in a formal way using a knowledge representation language. And a knowledge base can be used to produce more knowledge. And in particular, it can be used to be queried. I can send a query to a knowledge base. The knowledge base will do some inferences, some reasoning. It will provide me with an answer. So this works like a database. The difference between database and knowledge base is that a database uses information. So even though it's called database, it's actually an information base because we know the meaning of each part of data. You can query a database, but you will always get only the data that is present in the database. When you query a knowledge base, through reasoning, you will get information and knowledge which is not explicitly in the data, in the knowledge base. You will get knowledge and information obtained through the reasoning process. So for example, if I put into a database the information that Paris is the capital of France, and I ask, is Paris the capital in SQL, the database will reply yes. But if I ask, is Paris a town, then the database will not reply because this information is not included explicitly in the database. If it's in a knowledge base, and in a knowledge base, I can put the rule, all capitals are towns, then even though I have only the information Paris is capital of France, there is only one inference step necessary to the knowledge base to say it's a capital, all capitals are towns, donc, therefore, Paris is a town. So I hope now I made the difference clear and you see why we will use first order logic. So this is motivation. And now some very important concepts. All logics, because there's not just first order logics, there are many other kinds of logics which are less important but still sometimes widespread. All logic share three notions. Notion of syntax. When we write a logic formula, it has to be syntactically correct. It's like writing code in a programming language. It has to be syntactically correct, otherwise you cannot compile it. A deductive system, allowing you to do inferences, allowing you to obtain more formulas, allowing you to query and get answers. And a third notion called a model theory. And in a model theory, we have a notion of interpretation. So what does this mean? When you're doing math, for example, algebra, you only deal with abstract symbols. When you learn about groups and rings and fields, all you need is the definition, properties, special cases, and that's all. Here, we are interested in applying logic to different situations. So it's not only doing abstract calculations, it's applying these calculations to situations. So these situations will be in the real world, not necessarily in the real world. It can be in imaginary worlds, it can be in abstract worlds, and so on. But each time it will be taking formulas that are abstract and applying them somewhere. This operation is called interpretation. Interpretation is choosing a domain. A domain is a set of objects. For example, the real world. The real world is a very big set of objects and can be a smaller one. And for each constant in your formula, you need an object in this interpretation, in this domain. For each predicate, you will get a function. For each function, you will get a function, and so on. So each piece of your formula gets interpreted in some specific way. Now, once you have interpreted your formula, you get the notion of truth. If I take a formula, P of X, is this formula true or not? The question doesn't make sense. It's simply a logic formula. Once I have interpreted it, so once I have chosen a domain and I have interpreted what P is and what X is, then potentially I can say in this interpretation, the formula is true or the formula is false, or the formula may be true or false depending on some factors. So the notion of truth lives only in interpreted formulas, in interpretations, in domains. And whenever a formula is true in a domain, we will, in an interpretation, we will call this interpretation a model of the formula. So I know you have heard of models in different disciplines. For example, this afternoon, we will talk about the probabilistic model. This is a polysemic term. In this discipline, a model has this very specific meaning. It's an interpretation that makes a formula true. And here you have an example. This is a formula. It's syntactically correct. The plus is a predicate between X and Y. The equal sign is an ingredient. I mentioned it here. Now, is this formula true? I have to interpret it. If I interpret it in a situation where X and Y are equal to 2, then it's true. If I interpret it in a situation where X and Y are 1 and minus 1, the formula is false. So you see that this formula can be true or false depending on the interpretation. And we will say that a formula is a consequence of another formula if every model of the second is also a model of the first. So beta is a consequence of alpha if every model of alpha is a model of beta. What does this mean? It means that in every world, in every situation where the first one is true, the second one has to be true as well. And here you have an example. X plus Y equals 2, X plus Y positive. So in every situation where this is true, this is also true. The opposite is not valid. So this is a consequence going in one sense. Here you have the syntax rules of first order logic. The only thing to keep in mind is that predicates are always at top level and terms appear only as arguments of predicates. Or a special case, you can have term equals to term. So equals is a kind of predicate, but a very specific. It's hard-coded. It has a specific meaning, which is the same in all interpretations. While predicates, the meaning of a predicate is the one we give when we do an interpretation. So for example, loves, exists, are predicates. Father is a function because the input may be a variable or a constant or some other function, and the output is again a term. So intuitively, loves and exists can have values true or false in an interpretation. Father, the value of father is another object of my domain. If my domain is a domain of human beings, then A is the father of B, A is a human being, B is a human being. So this is a function. Do not confuse father with the predicate is the father of. In that case, if I say X is the father of Y, then is the father of is a predicate because it's either true or false. We would see examples. And here I'm resuming formulas and terms. So if we denote by PQR predicates, FGH functions, ABC constants, and XYZ variables, then this is a formula. You have predicates on the top level, variables as arguments of these predicates, and a connector between the predicates. Same thing here, you have a predicate and a quantifier. Here you have a predicate which has functions as arguments. Here you have the special case of the equality between terms. So in here they are terms, they are functions. And here you have an equality between constants. So these are formulas. These are not formulas, these are terms. So if I take just a variable, or a function applied to a variable, or a function applied to any combination of functions, variable, constants, I get terms. So in other words, this is wrong because equality is applied to terms, not to predicates. So this is not a formula. This is not a formula because you cannot have a predicate as an argument of another predicate. Predicates are on top level. This is not a formula because you cannot have a formula top level and you cannot have a predicate at argument. This is wrong. You cannot have a predicate equals something. This is not a formula because for all X expects a predicate and not a function. This is wrong because you cannot say for all predicates. It has to be variables. So you see all of these are syntactically incorrect. And this is typically something I can ask you next week at the exam. Is this expression a formula or not? So please try to get used of the role played by each one of these. The symbols I gave you are necessary for writing first order logic formulas. Now we can add new symbols to make formulas more easily understandable by humans. So here I have and, or, here is missing the symbol of double implication, sorry. And here I have the existential quantifier. These symbols are defined, and here I'm just missing again a symbol, sorry for that. It's the double implication symbol, the if and only if symbol with a single arrow. So these new symbols are defined out of the existing ones, and it's only for convenience of humans. This is the or, this is the and, this, the missing symbol here is the arrow in both directions, and this is the existential quantifier. And this is the syntax with the new symbols. As you have seen, we can apply quantifiers to variables. Whenever a variable is quantified, it's called bounded. Otherwise, it is called free. In a formula, we can, syntactically, we can mix bounded and free variables. So this formula is syntactically correct. But you see, you have an x here on the left and an x on the right. The one on the right is quantified. The one on the left is not quantified. Is this the same x? No. So this is syntactically correct, but it's a bad habit. It's not nice, not elegant. Whenever you have bounded variables, you can change their names. It's like having internal variables in a procedure. It doesn't really matter how you call them. And this is something you should do here to obtain this. And here there is no ambiguity. You have only one x and it's free. A statement having no free variables at all is called a closed statement. And I'll say clos. A closed statement, whenever interpreted, has to be either true or false. Once you have free variables, the value of the formula in an interpretation will depend on the values of the variables. Now, model theory is useful for interacting with the world. So imagine you have a robot like this one, which is called Shaky. And it's not a Dalek, it's just a robot. And this robot has to interact with its surroundings to take decisions on further actions. Interacting with the surroundings is getting data, knowing what data is, so having information, and extracting tendencies from information to take decisions on actions. So for example, if there is a hole in front of the robot should not advance. If there is a wall, the robot cannot advance, it should turn to a different direction. To do this, to take these decisions, the robot needs a representation of its surroundings. A representation that is simple enough to allow taking decisions and complex enough to allow the robot to survive and to do whatever its mission is. So it's important to have a representation language that is neither very complex, because this would mean many calculations and maybe useless pieces of information getting involved in calculations, and not too simplistic either, so that the robot can react appropriately to each event that may happen. In our case, we can use formulas of first order logic, and the surroundings of the robot will be our interpretation. It will be our domain. And the function going from these formulas to the domain is the interpretation function. What is a signature? Like in programming languages, a signature is just your vocabulary, the set of symbols you are using. In our case, it will be functions, constants, predicates. And for each one of them, an arity. How many arguments for functions, how many arguments for predicates. And what is a structure? A structure is whatever we need for interpretation, that is the domain, the signature, and the interpretation function. So what is an interpretation function? And this is very important to understand how it works. The interpretation function is applied to all ingredients of a formula. But for constants, it will send the constant to an element of the domain. And this is very important. Whenever you have a constant, you need to interpret it in some way. So you need to send it to some element of your domain. You can send all constants to the same element, it doesn't matter, but you have to send every constant to some element of the domain. Every function of your formula is sent to a function from the domain into the domain. So if I have the function father, in the formula, I call it a function because it only appears as an argument of a predicate and so on. When I interpret it, I send it to a function from the domain to the domain. So if the father of Pierre is Michel, then it sends Pierre to Michel. So it goes from the domain into the domain. And interpretation function sends this function to that function. Every predicate is sent to a function that goes from the domain to true or false. So there is this set of two things called true and false. And a predicate is always sent from the domain into true or false. Once we have defined interpretation function on all constants, functions, and predicates, then we can combine functions and constants and variables to obtain the interpretation of terms. And once we have interpretation of terms, we can combine interpretation of terms and interpretation of predicates and obtain interpretation of formulas. So by recurrence, you obtain the interpretation of a complete formula. And here I will give you an example. It's you may find it a bit long, but it will give you a better idea of what interpretation is. So imagine I have constants Roger, Baxter, Rougette, Bleuette. Imagine I have predicates man, woman, loves, hates. So man and woman are unary predicates. They take only one argument. Loves and hates are binary. They take a first and a second argument. So I can write formulas like man Roger, woman Baxter, loves Roger Roger, hates Bleuette Roger, and so on. These are just formulas. They are correct syntactically because predicates are top level and my constants are arguments. Now, I want to take an interpretation of these formulas. First, I need to choose a domain. Let's take this as a domain. I'm using pictograms to show you that these are just elements of a set, whatever set, be it in the real world or in an imaginary world, it doesn't matter. I'm sending Roger to this guy, Baxter to this guy, Rougette to this, and Bleuette to this. This is just a choice. And it's part of my interpretation. I'm sending predicates, man and woman, to functions going from the domain, this, into true or false. So this means true, and this means false. So I of man is a function. How do I describe a function? By its values. I have 4 elements in my domain, so by giving the values of these 4, I get a complete description of my function. Here it is. And here is another complete description. So there is a way of saying Roger, man Roger is true. Man Rougette is false, and so on. Binary predicates, loves and hates, are sent to functions going from the domain times the domain into true, false. So who loves whom, who hates whom. And here I have the complete description of these 2 functions. I can use set theory to describe my interpretation. So I'm using a potato for the domain. I put my 4 elements of the domain, the 4 known elements of this domain, into this potato. And these are men, these are women. So the elements that make this predicate true in the interpretation are subsets of the domain. So whenever you have a unary predicate, this unary predicate corresponds to a subset of your domain, the subset of elements for which the predicate is true. So here you have the predicate man, and here you have the man of this domain, and predicate woman, and here the subset of woman of this domain. Whenever you have a binary predicate, it can be represented by a subset of the square of your domain. Okay, so these are all pairs of elements of your domain. Some of them are true when we apply the predicate loves to them. Some of them are true when we apply the predicate hates to them. And some are both, and some are none. So we have a set-theoretic view of interpretation. We can understand interpretation using set theory. So I will finish this, and then we can take a break. So what do I mean by set-theoretic view? Interpretation is an abstract notion. It's a function that goes from a formula to a domain. It sends ingredients of your formula to functions in your domain. There's another way of looking at it. It's using set theory. So to every predicate, we can assign a subject to any unary predicate, we can assign a subset of the domain. It's the subset of elements that makes the predicate true. If I take the negation of my predicate, then the subset is the complementary set of the previous one. So you see, a predicate, a unary predicate corresponds to a subset. The negation of a unary predicate corresponds to the complementary set. If I take this is a predicate. It's a predicate that is always true. It corresponds to the domain. Why? Because if I ask the question, for which element is this predicate true? The answer is for all elements, for the whole domain. This false can also be considered as a predicate that is always false. So what is the corresponding subset? It's the empty set. So this corresponds to the domain, and this corresponds to the empty set. Now, if I take the conjunction of two predicates, P and Q, I have a subset for P, a subset for Q, and saying P and Q is the intersection. So these are the elements for which both P and Q are true. So interpretation sends a conjunction to an intersection of subsets. Similarly, if I take disjunction or P or Q, I get a union of subsets. So these are the X's for which P is Q or Q is true. And this is the part where both are true, but it doesn't matter. The blue part here is P or Q. What is implication? Implication, we haven't seen it yet. It's one of the next slides. An implication is true an implication is true either when the left part is true and the right part is true, or when the left part is false. What does this mean? Well, either I have the left part true and the right part true, and this gives me the intersection of the two, or I have the left part false, so this is all the complementary of P, and in that case, I don't care about the right part. So I know it's not very intuitive, but you should think about this. This blue part is the set-theoretic correspondence of P implies Q. And when I have a double implication, here I got the symbol, then it means that either both are true or both are false. This is more intuitive than that one. Now, there's a special case of first-order logic, which is called propositional logic. It is much simpler. You have no predicates, you have no variables, no functions, no quantifiers. You only have predicates of arity 0, which are called propositions. So A is a predicate of arity 0. So it's something which is either true or false in the interpretation. But it doesn't take any arguments, it doesn't have function, doesn't have quantifiers. In propositional logic, something can, the interpretation, the only thing we can interpret is saying if something is true or false. And then we can combine truth values. And here is the, here are the truth values of the implication. So as you can see, whenever A is false, A implies B is true. And whenever A is true, A implies B is true only if both A and B are true. Otherwise, it is false. And from this table, you see that I have introduced these symbols, and here it's missing the double implication symbol. Sorry for that. I could define more symbols with all combinations of true and false values, but it won't be very interesting. So only these are really useful, and only this one is necessary. And truth tables allow me to calculate truth values of complex formulas. So I start by giving truth values of my propositions, and then I take intermediate formulas until I get the complete formula. And this formula has the particularity of being always true. So whenever I interpret, I can choose whether a proposition is true or false. But if I take this formula, I don't have the choice. If I take this formula, it will always be true in all interpretations, and it's called a tautology. So please do not confuse first order logic and propositional logic. Propositional logic is a special case. Interpretation still exists, but it's not something as general as in first order logic. It's something very specific. All you can do is choose values true or false for your propositions. It can still be useful as a knowledge representation language, but it has less representative power than first order logic. And I'm giving you propositional logic only as an example, and because you probably already have seen these notions, so that you can compare the two and realize that first order logic is much more and gives you much more power to interpret your formulas. Okay, it's time to take a break. So we will start again in 15 minutes. So now it's 10:53. We will start again at 10. Well, let's say 10 minutes past 11. See you in a moment. Okay, so I hope you have a nice break and got a cup of coffee like me. You may consider that I'm spending a lot of time on the notions of interpretation and model and first order logic. It's the kind of notion which is trivial once you have understood correctly what it is, and which can be very obscure if you haven't yet understood. So please spend some time to be sure that you really understood these notions. And to show you that they are not always very intuitive, I have here a small test. So I told you that a tautology is a formula that is true in all interpretations. For example, if I say P of X or not P of X, so since either P, so P is a predicate, either P is true in some interpretation or is not true, but if I say P or not P, then in both cases, one of the two will be true, and so this formula will always be true. And it's called a tautology. Now, I'm asking a question. This is a test. Let us take the formula. There exists an X such that X is equal to Mainzelmännchen. Mainzelmännchen are the equivalent of the French Shadok, and they lived in the second German channel, CDF, in the 60s and 70s. So it doesn't matter what a Mainzelmännchen is. The question is this formula a tautology or not? So intuitively, you would say, no, not at all. It depends on the interpretation. If I interpret this in a domain where there exists Mainzelmännchen, then it's true. Well, actually not, no. Here, Mainzelmännchen is not a predicate. It is a constant. So maybe this is something I should have told you. In this formula, X is a variable and Mainzelmännchen is a constant. So intuitively, you would say, okay, then it's even more depending on the domain. Well, actually, no. Look at the definition of an interpretation. An interpretation function sends constants, and this means all constants of the signature, into the domain, all of them. And when a function sends something, it has a target. It has to have a target. If you say my function sends this constant to nothing, then it's not a function. Okay, so whatever the interpretation of this formula, since we have written Mainzelmännchen in the formula, it is a constant of the formula and we have to send it somewhere. So our domain will have at least one element, and we will send Mainzelmännchen to this element. If it has more, then even better. We will send it to some element. And the formula says there exists a value of the variable X, and this value is equal to Mainzelmännchen. Does this value exist? Yes, since we have sent Mainzelmännchen to some element of the domain, there is some element that has the value Mainzelmännchen. So this formula is always true by the definition of what an interpretation function is. Okay, so this has absolutely no scientific value, this slide. You will never use it in your life, but the purpose of this slide is to make you think about what an interpretation is, and if you have figured it out correctly. And now you know what a Mainzelmännchen is, and it's a reference to Heinzelmännchen, which are traditional figures of the town of Köln in Germany. And Mainz, like the town of Mainz, where the second television chain was located. Okay, so let us continue. We already defined what a model is. A model is an interpretation for which a formula is true. A consequence is a relation between two formulas. Beta is a consequence of alpha is if every model of alpha is a model of beta. So in every world where the first one is true, the second one is necessarily true. And we use this symbol. And this symbol looks very much like this symbol. Do not confuse them. This one means every model of alpha is a model of beta. So here we are doing interpretations. This one means that beta can be proven out of alpha by a sequence of inferences. Here we are in the abstract world. So here we are in model theory, here we are in abstract theory. But it has been proven that for first order logic, these two are equivalent. And this makes first order logic useful because you want to know if some phenomenon is a consequence of some other phenomenon, a necessary consequence. You formalize the first one, you apply inferences, you prove the second one out of the first, and then you interpret it. What you have done is equivalent to showing consequence. So there is between the two worlds, the world of model theory and the world of abstract theory, an equivalence as long as we are using first order logic. One way of interpreting consequence is saying that we have an implication that is true in every interpretation. And here we have the proof. So this is, again, not to confuse implication, which is just a new formula out of the old ones, and consequence, which is a relation between two formulas. Now, let us look at natural language, because this is our goal. We want to formalize natural language using first order logic. Whenever we have declarative sentences, they can be, most of the time, if they are simple enough, they can be interpreted, they can be interpretations of a formula. So if I say Michel is a student of EMT Atlantique, I can formalize this by a sentence. Trump has won the election can be formalized by a formula. It's not necessarily true. Truth depends on interpretation. Okay, and Trump has played a lot with this. That the fact that truth is relative to the interpretation. So whatever Trump has said is true in an interpretation which is not necessarily the real world. Okay. Connectors of and or are used to formalize conjunctions and or in natural language. Sometimes when we use an and in natural language, it means more than a conjunction. This is something we will see next week when we will talk about pragmatics. So for example, if I say, I saw Michel and I greeted him, then this and is not simply a conjunction. It's not simply the fact that I saw is true, I greeted him is true, but there is also a temporal order. I first saw him and then greeted him. These are called implicatures. These are additional information we put into natural language that is not explicit. And of course, first order logic can formalize both just the apparent part of a sentence and also the hidden meaning of the sentence. We also use implication for conclusions, but be careful, as we said, implications are true when left part is true and right part is true, but they are also true in logic when the left part is false. So this formula, cocks are laying eggs, implies that IMT Atlantique is an engineer school, is a true sentence in the real world. Also, donkeys fly implies that IMT Atlantique is a discotheque, is also a true sentence in the real world, because it's an implication, the left part of it, which is false. The universal quantifier is interpreted in natural language by every something is something else. But when we have sentences like this, the formula, the formalization of this sentence will use an implication. So it will not use a conjunction. Do you see the difference between these two formulas? This one means for every value of the variable x, whenever this value is a man, then the same value is a mortal. And this is what we mean when we say every man is a mortal. This one says for every value of variable x, x is both a man and a mortal. This means that all elements of our domain are men and mortals. This one means in my domain, I may have other elements which are not men and for which I don't know whether they are mortals or not. Okay. Is this true? It depends on the domain. If I take the domain of man, and of course I mean man and woman, then this is true. But it doesn't give me a lot of information. I know already that my domain has only man, and this says for every x, x is a man. Okay, this is redundant. This one is interesting because in a domain which is much larger than the domain of man, it's the real world, it's saying that the subset of your domain that consists of man, well, all of these men are mortal. In a symmetric way, when we use an existential quantifier.
Excuse me?
Yes?
Could you just say again what the second sentence means? Yeah.
The second sentence means that for every value of x, this value is both a man and a mortal. So all elements of my domain are men. This one is selective. It says among all elements of my domain, and these elements can be man, animals, chairs, tables, computers, ideas, sentiments. Among them, if I take man, then these are also mortal. So all men are mortal. This one says my domain has only men, nothing else. And these are mortal. Okay.
Okay, thank you very much.
So same thing here. When we use the existential quantifier, we combine it with the conjunction. The sentence, there is a student of IMT Atlantique called Xavier, is formalized by there exists an X such that X is a student of EMT Atlantic, and the name of this X is Xavier. So do not use the implication. So what does this formula mean? This formula says that there exists an X such that either X is a student of EMT Atlantic and his name is Xavier, which is okay, or this X is not a student of EMT Atlantic, and in that case, we have no idea about his name. Okay, so something useless. The order of the quantifiers is very important. Here you have two formulas where I have inverted the order of the universal and existential quantifier. Do you see the difference between them? This one means for every X, there is a Y, and this Y, since I have mentioned X first, this Y depends on X. There is a Y such that X loves Y. So everybody, there is somebody, for every X, there is a Y that is loved by X. And this one says there is an X that is loved by all Ys. So here there is an X, the same X for all Ys. So, so this X loves all the Ys. Okay. But you know this already from mathematics. You know very well that between for all X there is an Y such that f x, y is something is not the same thing as there is an x such that for all y. For example, in the formulas of limits, of continuity, and so on. This is a very interesting slide because I'm explaining what equality is. And you have learned equality, if not in kindergarten, at least in primary school. And now, after so many years, I'm here to tell you what it means. So equality in first order logic is a kind of predicate with a very specific meaning. The meaning is that when I write that x is equal to y, it means that in my interpretation, I have to take the same element for both. So this is a restriction on interpretations. When I say A equals B and A and B are constants, you know that to make an interpretation, I need to choose values for A and B. When I say A equals B, I have to choose the same value of the domain for A and B, and this for all interpretations. And if I take the negation of this, it means that I have to choose different elements of the domain in every interpretation. And this equality relation allows me to introduce uniqueness. Saying that something is unique is saying that for all other constants, no, it allows me to introduce difference. So here to say that A has at least two brothers, I will write there is an X and a Y such that brother X is brother of A and Y is brother of A, and X is different than Y. If I use only these two, then in some interpretation, somebody may choose the same value for x and y. By adding this condition, x and y must be different. Now here, as very often, I have a trap. Does this sentence really mean that A has at least two brothers? Okay, when I'm asking the question this such a way, it means that obviously no. But why not? What is the trap? The trap is
A could be X or
yes.
Y.
What
A
did you
could
say?
be X or Y.
Exactly. I haven't mentioned A. And A could be X or A could be Y. In the real world, it doesn't make sense to say that somebody is himself's brother. We always have the background knowledge that the brother of somebody is somebody different. Okay, there is only a movie called Predestination where this is all mixed up because it's a movie made with time traveling. And after you've seen the movie, you find out that all persons you saw are in fact the same person that kept going back into time, changing sex, and being the father and the mother of himself and brother of himself, and so on. So only in that movie, you have somebody being his own brother. Here, we didn't mention it. So it could be that A and X are interpreted by the same value. And in that case, A doesn't have two brothers because in one of the two predicates, X is equal to A. So to make this formula complete, I should add also and X different than A and Y different than A. So let us take some proverbs and try to formalize them. Old habits die hard. To formalize, I first need to choose a domain. Here I can take the real world because habits are parts of the real world and dying is part of the real world. What will be my predicates? Since my domain is the whole real world, I have to specialize to habits and human habits because this proverb is talking about humans. So I need a predicate for something being a human habit, something being an old human habit, and something, the same thing, dying hard. I will not specialize this in dying and dying hard. I take a single predicate for that. And the formula will be for all X, if X is a human habit and X is old, then X dies hard. So you see, I have a universal quantifier and I use an implication. This is specializing who am I talking about, and this implies that these values of X have this property. Better late than never. I can take as a domain the domain of actions because it's not said, but it's sous-entendu that we are talking about actions. So we have a predicate of doing an action in a late manner, never doing it, and we also need a predicate for better. So what will be the arities? This one and this one have an arity of 1 because they are properties of actions. This one has an arity of 2 because we are comparing two actions. So now that we have our predicates, you can already guess the formula for all x and for all y. If x is an action that is late and y is an action that is never done, then x is better than y. Okay, this means that no matter what the actions are, an action that is late is better than an action that has never occurred. You can't have your cake and eat it too. So this is the English version of on ne peut pas avoir le beurre et l'argent du beurre. Breton proverb, since butter is very important in Brittany. And cake is very important in the English spoken world. The domain will be again the real world. I will not interpret this metaphorically. I take the literal meaning of the cake. So I need to specialize on cakes, and I have actions to have and to eat. So a possible formula will be for all x that are cakes, you cannot have, so not having x and eating x. So of course, this formula can be written in different ways. This is maybe one of the shortest ways, and it's very close to the natural language representation. All that glitters is not gold. So I've chosen this one because it's a bit tricky. My domain will be the real world. My predicates will be something glitters and something is gold. I don't need to specialize because in all, there is no indication about what we are meaning. Is it an object? Is it an idea? Is it a human being? It's not specified. And here is a first possible interpretation of this formula. For all x, glitters implies x is not gold. Is this formula correct? Does it represent the proverb?
No.
I don't think so. Oh, I'm sorry.
No. So what does it represent? What does it say?
That everything that glitters isn't gold, not that all that glitters is not gold. Like,
yes, okay. So the two sentences are very close.
yeah, like if it glitters, it's not gold. But here it says like, yeah, I'm sorry.
So here you see an example of the ambiguity in natural language. And what this formula says is whatever something glitters, it is necessarily not gold, which is false in the real world because gold does glitter. Okay, so what we want to say with this sentence is that there are some things that glitter and they are not gold. We can even mean the majority of things that glitter are not gold. We can even say only gold glitters, which is not true either. So what we really want to say is there exists an X which glitters and is not gold. Okay. So here is one possible interpretation of this sentence. I think it's a correct interpretation. Maybe the sentence has more meaning, which I haven't given, so it's maybe a partial interpretation, but at least I think it's a correct one. And if you interpret this literally, you get much less than the proverb. There is something that glitters and that is not gold. Okay, and so what? A famous saying by Socrates, not the football player, but the philosopher: one thing only I know, and that is that I know nothing. And neither uden either. Domain, the real world. Now, can I formalize this? What I will formalize is I know only one thing, first sentence. I know nothing, second sentence. Okay. I cannot formalize the fact that the thing I know is the fact that I know nothing. Okay. This needs higher logic, more than first order logic. So let me formalize this sentence, which is a bit weaker than that one. I take predicates knowing and predicate of thing. And the first sentence will be, there exists an X that I know. And for all Y that I know, Y is equal to X. So this is uniqueness. And this is even a bit stronger than this sentence. This sentence says, I know only one thing. It doesn't say that this thing exists. I should have written, there is one thing I know and it's unique. Second sentence says, I know nothing. There exists nothing I know. And if you look at these two sentences, you will see a contradiction because you have a predicate and the negation of this predicate. If you have both together, you get a contradiction. So this formula is false in all interpretation. It's called a contradiction. Okay, so does this mean that Socrates is saying nonsense? No, it means that there is more in this sentence than this formalization. This formalization is useless since it's a contradiction, and we need either better understanding or a better logic, a higher logic to represent this in a meaningful way. In this slide, I'm giving you some tools for making calculations. It's something the machine can do, and the machine does very well. And these rules have names. It's either properties of connectors, commutativity, associativity, or properties of relation between interaction between connectors and interaction between connector and quantifiers. So we said that a tautology with a Y is a formula that is true in all interpretations. So this means that all interpretations are models. We will say that a property, a formula is satisfiable, satisfaisable in French, if it has at least one model. So if there exists at least one interpretation in which it is true. Otherwise, we will say it's unsatisfiable. Like this guy who can get no satisfaction. And in that case, we would say it's a contradiction. When we take statements and we take all possible consequences, then we get a theory. And these statements are called theorems. So you see, a theory can be either a set of actions and we apply inferences and get all possible formulas, or again axioms and then taking consequences of these axioms. So now we are in a domain and these consequences are other formulas which we call also theorems. And the set of all theorems is a theory. A knowledge base is a conjunction of formulas. A knowledge base can have models or not. Okay. So whenever we have an interpretation that is a model for a knowledge base, then this knowledge base becomes interesting because it tells the truth about this particular interpretation. Now, what we want to know, and this is the crucial question in knowledge representation, is whenever I have a statement and a knowledge base and an interpretation of both the knowledge base and the statement, do I have a consequence? Is my statement a consequence of the knowledge base? So take, for example, science. Science is about the real world. In science, we have theories. Theories means we started with actions and we observed consequences and we got many possible consequences, many possible theorems. And now I'm arriving with a new statement. What I want to know is my statement a consequence of all the statements that others have already established? In that case, my statement can be added to this knowledge base, or at least can be inferred from this knowledge base. So it's part of this theory. And this is what we do when doing science. So how do we establish this relation of consequence? The difficulty is that when we say that we have a consequence, this should be the case for every interpretation. How can we prove something for every interpretation when we know that there can be infinitely many interpretations? Interpretation is like imagination. You can imagine possible worlds. Your power of imagination is infinite. You have to prove that this formula is true in every possible and imaginary world whenever the knowledge base is also true. So you cannot prove this directly. But you have this theorem that says that when we take first order logic, then consequence and deduction by inferences are equivalent. In other words, in other words, whenever I can prove that I have a formula out of the formulas of the knowledge base, then it's a consequence of the knowledge base. And these two are equivalent. So to show whether this crucial question is true or not, I just need to deduce my formula by a sequence of inferences, or show that I cannot deduce it by a sequence of inferences. So what we need now is a deductive system that allows us to prove deductions and therefore to prove consequences. And here is a theorem which is very important because it allows us to do calculations. So this theorem says that we have a consequence, any consequence, but also in our case, a consequence between a knowledge base and a formula, if and only if the conjunction between the knowledge base and the negation of our formula is unsatisfiable. So all you need to do to prove that alpha is a consequence of the knowledge base is to take the negation of alpha, add it to the knowledge base, and show that you got something contradictory. And this a machine can do, because there are ways of showing that some conjunction of formulas is a contradiction. Now, to do this, we simplify our formulas. In the next slides, you will see 1, 2, 3 ways of simplifying formulas, and these are used by machines to prove that there is a contradiction. So you will perhaps not use these directly, but it's good to know them, gives you a better idea about how the machine works. The first way of simplifying formulas is writing them in Prinex normal form. Prinex normal form means that all quantifiers are at the beginning of the formula. So take any formula, and there is a way to push all the quantifiers to the beginning of the formula while keeping equivalence. So I'm not obtaining a different formula, I get a formula that is equivalent, but with the quantifiers at the beginning. For every formula, there is an equivalent formula in Prinex form. There is an algorithm for doing this. The algorithm says whenever my variables are quantified, it means they are bounded. And if they are bounded, I can change their names. So here, this x is not the same x as that one, in the sense that here is a quantifier for this x, and here is a quantifier for that x. So I can rename this x and this y into, for example, u and v. Now I have here for all u, and here there is no u. So I can push this u here to the beginning of the formula. Not entirely beginning, because I already have some quantifiers, so it will be after those quantifiers. But since there is no u in this part of the formula, it doesn't change anything if I push u to the beginning. And by doing this, I get all the quantifiers at the beginning. The next step is to convert the formula into conjunctive normal form. Conjunctive normal form means I have a conjunction of disjunctions. So I have parentheses. Between parentheses, I have conjunctions. And inside parentheses, I have disjunctions. And again, there's a theorem saying that every statement without quantifiers is equivalent to a statement in conjunctive normal form. And here's the algorithm for obtaining it. It has 4 steps. First step, take all the double implications. You see, I've recompiled the document, so now you see this symbol. So all double implications are replaced by conjunctions of simple implications. Here, this double implication becomes right implication and a left implication, since I'm inverting here the order of my arguments. I replace implications by negation and disjunction. Tak. I enter negations into parentheses. So here I have this negation outside the parentheses. If I enter it using De Morgan laws, I get this. And finally, apply the distributive property. So this B here can be entered into the parentheses as not F or B and not G or B. And you see after these steps, I got 3 expressions in parentheses. Between the parentheses, I have conjunction. Inside the parentheses, I have disjunctions. And now you see how useful this is for the machine, because this quite complex formula, which is useful for the human to understand, becomes this much longer formula, which is opaque for humans. But for a machine, it's just a conjunction, 3 things. For this formula to be true, all 3 have to be true. And each one can be checked separately. And if one of these 3 can be proven to be false, then the whole formula is false. And hence, it's a contradiction if we prove this in all interpretations. Okay, so you see the interest of doing these 2 steps. And then you have a 3rd step, because don't forget that we have placed quantifiers at the beginning. So even if we do this, we will still have our quantifiers waiting to be processed. And this final step is called skolemization, from the name of a mathematician called Skolem. And skolemization is eliminating all the existential quantifiers, keeping only universal quantifiers. Now, skolemization does not produce an equivalent formula. We are losing information. But if a formula is satisfiable, then its skolemized version is also satisfiable, and that goes in the other direction as well. So we don't get equivalent formulas, but from a contradiction, we will get a contradiction. From a tautology, we will get a tautology. From a satisfiable formula, we will get a satisfiable formula. So at least we can prove contradiction doing skolemization. Now, what is skolemization? This is also quite interesting as a notion. Imagine you have your formula with your quantifiers at the beginning. So it's in pre-next form. I don't really care whether it's in conjunctive form, but okay, we can always consider it's in conjunctive pre-next form. Now, if all quantifiers are already universal, then I'm done. There's nothing to skolemize. If this is not the case, it means that I have at least one existential quantifier. There are 2 cases. First case, my existential quantifier is at first position. If it's in the first position, it means that all the other quantifiers depend on this first one. Sorry, no. If it's at first position, then it says there exists an X such that for all Y, for all Z, and so on, I have the formula. What I do is I replace this X, which is existentially quantified, by a constant. I give a name to this constant. It must be a new name. This constant must not be present in the formula. And now I remove this existential quantifier in the variable. So I replace the variable by a constant. Intuitively, this means if there exists such an X, then I can give it a name. I can choose one of its values, because when I say it exists, there may be more than one values of X for which this happens. I choose one value and I give it a name. And this will be a constant. And I replace my variable by this constant. So I get a formula which is less general. Okay. But if the original formula was true, this new formula is true as well. Okay. Now, if my existential quantifier is not at first position, it means that the variable is a function of the previous variables. Remember, when we say for all X there exists a Y, then this Y depends on the X we have chosen. So in this case, I replace the variable that is existentially quantified by a function of all previous variables, all universally quantified variables. And by doing this repeatedly, I eliminate all existential quantifiers. So the variables that are existentially quantified are replaced either by constants or by functions of other variables that were quantified before. Let us take an example. And this is part of a lab, which we won't have the time of doing, but you will find on Moodle. And it says all those who love all animals are loved by somebody. So all those who for each animal love this animal, there exists somebody who loves them. Okay, so this is first order logic formalization of this sentence. I start by eliminating implications and so on, and I get a formula which is not yet conjunctive, and here I have a formula where I have here universal and here an existential quantifier. So this one is in second position. So Y depends on X. I will replace Y by a function of X. So Y disappears and I get a new function, a function that doesn't exist before in my formula. Here, same thing. This Y depends on X. So I replace this y here by a function of x, and it's not the same function as here. We call these functions Skolem functions, and when we use constants, then we call them Skolem constants. So another example, if I have the formula cosine of x equals 0, and I use an existential quantifier. So I have the formula, there exists an x such that cosine of x equals 0. You know that there are many x, there's an infinite amount of x's for which this formula is true. I want to eliminate the existential quantifier. I can choose one value, for example, p divided by 2, and this p divided by 2 will be the Skolem constant, which will eliminate the existential quantifier. So the Skolemized version of there exists an x such that cosine x equals 0 will be, for example, cosine of p divided by 2 equals 0. I eliminated the existential quantifier. I got a formula that gives me less information than before. It gives me only one possibility, but this was a way of eliminating the existential quantifier. Up to now, we only studied original, authentic first-order logic, in which we have domains, and domains have elements. There is another version of first-order logic which is combined with types, which is called typed first-order logic. And here, all constants and variables belong to types. Necessarily, functions and predicates have signatures. So each argument must belong to some type. And in the case of functions, the output must also belong to some type. And if we consider true and false of being a special type called Boolean, then there is no distinction anymore between functions and predicates. Predicates are just functions with a Boolean output type. In the lab, for which you will find the support on Moodle, I introduce you to a tool called Z3. So Z3 is a theorem prover in typed first-order logic. It's a Microsoft product. I don't like Microsoft products, but this one is freely distributed, so why not using it? It works fine. It has a Python interface, and we can use it, for example, for this paradigmatic case of saying Socrates is a human. All humans are mortal. So this will be my knowledge base. And I'm asking, here is my query, is Socrates mortal? The machine should tell me that yes, by using these two, applying a modus ponens to these two, I obtain that Socrates is mortal. Here is how I do it. I define a type called human, and Socrates will be of this type, and my variable x will be of this type. Then I declare functions, which in fact are predicates, since their output type is Boolean, and their input type will be human. So is human is a function going from humans to Booleans. My three formulas So this is my knowledge base, and this is the negation of my query. Why negation? Because remember, showing a consequence is equivalent of showing that knowledge base and negation is a contradiction. So I'm taking the negation of my query. Socrates is not mortal. I'm writing this in Z3 Python syntax, which is not such different than usual syntax. Is human Socrates. For all x, I have the implication is human implies is mortal, x, and the negation not is mortal Socrates. So I'm giving all this to Z3, and Z3 answers unsatisfiable. This is unsatisfiable, it's a contradiction, so mortal Socrates is a consequence of these two. And here you have the complete code in Python. I just import all classes. I declare a type, a constant in this type, a function from this type to Booleans. I instantiate a solver, a theorem prover. I instantiate a variable x of this type. So don't be abused by this. I don't know why they've chosen this. In fact, it means that x is a variable. I don't know why they're using this name constant. And I'm adding 3 formulas to my knowledge base, and I'm asking for a check whether it's satisfiable or not. And I'm getting the answer, it's unsatisfiable. And in the lab, you have here something which is still close to linguistics, since we have sentences and we want to prove something out of natural language sentences, and also some other problems that have nothing to do with natural language processing. At least these two, 8 queens and magical squares, they are just to show you the possibilities of Z3. And here again, I have problem with dragons. Show that smart dragons are not endangered by tourists. So I encourage you to do this lab by your own. Using Z3 will allow you to prove formulas. So first you have to formalize sentences into formulas, and then with Z3 you can check whether your formalization is correct or not. And having you discover Z3 is not innocent. This is something you could potentially use in your chatbot if you want to include reasoning. So if we want a reasoning chatbot, then we have to extract knowledge from our domain and extract information from interaction with humans, formalize this information, and then do inferences. So you don't have to. It would be a very clever chatbot, and most chatbots today are not reasoning. We are not yet there. But you could try it out with some simple case. And in a forthcoming lab, we will see how to use another tool, namely ontologies, also in doing reasoning. So this is a first tool for knowledge representation. It's a very powerful tool, and therefore it's not very widespread because some may think it's too powerful. And in a forthcoming lecture and lab, we will see another representation language, which is description logics, and another tool, which is ontologies, used in the semantic web. And in that case, we will have a lab on question answering systems using ontologies. So once again, an application of these tools into chatbots and artificial intelligence. I have again 2 questions for you, and I hope this time you will answer them. They are quite simple. So let me make them visible. Here you are. Are there any questions for this, what we saw in this lecture?